We're kind of doing them concurrently. The motion packet, at the very beginning, there was that big old blank space. And the big old blank space says there are 3 closely related concepts you need to keep straight when dealing with motion. We talked about the 3. What are the 3?
Position, velocity,
Yeah, you guys haven't written it down yet. You should have written down position, velocity, and acceleration. Now with your position, velocity, acceleration, last semester, we moved through this list. Last semester, I'll do it in green because it's review. We moved through this list step by step, going from position to velocity and from velocity to acceleration. Why?
by deriving.
By deriving, differentiation, yeah, because a derivative is a rate, right? And so if I wanted a rate of change of position with respect to time, where did that get me? Velocity. Exactly. So I would take a derivative, I would take d dt of position, I'd end up with velocity, who is dp dt, dx dt, ds dt, the derivative of position. And then how would I go from velocity to acceleration? Take another derivative, because acceleration is the rate of change of velocity, how quickly velocity is changing, positively or negatively, as my object was moving to the right or to the left. Now, this semester, what have we been able to do thus far? And the example we just looked at is an example. How were we able to go from acceleration to velocity? The antiderivative or integrate. Good. And then how can we go from velocity to position? We integrate again. So now we're able to not only go forwards, but also backwards as well, because an integral takes a rate, takes a derivative, anti-derives, and says, or asks the question, who are you the rate of? What quantity are you the rate of when we integrate? Now, hold on, I was just talking about hit the ground. Do you guys see hit the ground anywhere? No. But there is something that means the same thing. Not initially, not at rest. At the origin. Now, at the origin is specifically talking about a type of problem where a particle is moving on an xy axis. And not just on an xy axis, because we are only dealing with motion, just to keep it simple in a physics sense. We're only moving right-left, only horizontally, or vertically. We're not moving both, because I kind of introduced last semester. In order to move horizontally and vertically, like to go to the right and up, or to the left and down, or to the right and down, we would need parametric equations. We need x of t, y of t from last year, and the derivatives get a little bit trickier. That's more like calculus stuff. Still good and not super complicated, but just beyond where we are right now. So we're just moving right-left, or just moving up-down. And if there's a particle moving on, for instance, the x-axis, right-left, the origin would be
0.
Indicated by, what would be 0 though at the origin?
The position of t.
The position. Because it could be going through the origin with a speed or with a velocity, which is speed with direction. It could be going through the origin with a velocity and or with an acceleration, but what we do know at the origin means position is equal to 0. Now guys, from our forever card, when else do we say that position equals 0? Hit the ground. So that's how I was tying them together. Hit the ground is when position equals 0. Doesn't mean how fast the object is going when it hits the ground. Same thing as we don't know how fast the object is going if it just says at the origin, but we do know position is equal to 0. So that's getting us ready for letter C. For letter B, letter C, we're going to let position equal 0. But for letter B, why did we let velocity equal 0? How come?
Because when the velocity is 0, it's going to start falling.
When the velocity is 0, it's going to change from rising to falling. Now, what I'm showing you is technically two-dimensional motion. So think about, okay, the object is going up, and then when is it going to come back down? At the very top of that motion, if you were to graph that with respect to time, is going to be a horizontal tangent line. Velocity is 0. Velocity is positive, it's going up. Velocity is negative, it's going down. There's a 0 in between by what theorem?
EVT.
IVT. EVT is the extremes, the absolute maximum. IVT says if it's going from a positive velocity to a negative velocity, there has to be a 0 in between. So We set the velocity from, in letter B, we need to set the velocity equal to 0 and then plug in. We found the position function, we have him ready to go. Our initial position was 0 because it said that it was launched from the ground. So all we need to do to plug into this is have a t, and we won't have a t until we solve for t. And so we need negative 9.8 t. What was the rest of our velocity equation? Plus 33 plus the initial equals 0. So then t is going to equal 33 over 9.8 seconds. That's when it's going to be at the top of the motion. So all we need to do in order to find the position would just be to go ahead and plug into x. So we would take that time. Why am I plugging it into the x again? What was the wording in?
How high?
How high. Good. And then specifically in this one it would be meters, right?
Yes, meters.
Okay. You guys need to have your calculators out. Maybe some of you are already plugging in so that we can double check each other. Actually, go find mine too so that we can all be on the same page. If you're going to be using the same equation over and over again, maybe it's something where, like for instance, I see we're going to use position in letter C, and if this was like a big old FRQ problem with an A and a B and a C, you might just want to put this equation for position if we're going to use it multiple times in your Y1. That might be helpful if mine didn't. Negative 4.9 t squared plus 33t, which we're just going to call x. Initial position was 0, so we're leaving it. And then guys, how do we do cool plugging in stuff in our calculator?
Pairs, y pairs.
Yeah, you can use that cool alpha y equals over to trace y1 of 33 divided by 9.8. You guys double check my math. I think I'm getting 55.561.
Yes.
So 55.561 meters is how high this, to the ball, rocket, launch, ooh, projectile, who knows? So then how do you use your calculator? Help me out. We have this function for position in my Y1. How do we use it to find the zeros, aka when, to find when it hits the ground?
When the position is 0.
Good. But how do I use my calculator to do that?
You can use the
Graph it.
and then
Okay, so if we graph it, I'm just going to hit my graph button. I'm in Zoom Standard right now. 10 by 10 window.
Oh boy.
Problem is, I don't see my full parabola, but what am I going to do with that graph? I could zoom, but what am I trying to find again?
Zeros.
when it crosses.
So, do you guys see a cross? I see a cross.
Cross.
How are we going to find that cross?
We're gonna find
Two.
intersect.
Good, we're going to go to second trace. Intersect is if we had a second curve, but I could use zeros. The question says left bound. You guys remember how we do left bound, right bound? Follow the little cursor.
Holy moly, it's just gone. There.
And I have my little cursor right before the intersection. It's the little blinky button. I'm going to hit enter. And then I go my little intersection after, and then the 0 ends up being 6.735.
Yes, sir.
Now here's the dilemma. Why am I not going to box this answer?
Because
That's
just the
what we're
time.
looking for.
Because we're not asking for, they're not asking for when. They're asking for,
The speed of this
okay, so where am I going to plug this when into?
velocity.
Velocity. So velocity of 6.73. Now I'm going to actually put a dot, 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 because this is not my final answer, so I don't want to round this final answer. Does anybody know how to keep this little number that's on my graph right now for my 0, how to keep him, how to stow him, and then be able to use him?
You could just click stow and then a variable.
You can't hit stow right now on the screen.
Oh.
But if you just solve for something, an intersection, a maximum, or a minimum, and it still says 0, it's established it, I found it, like this is the answer.
To memorize.
If you, well, you could memorize it, you could write it down, but we don't actually have to write down a million trillion decimals for the AP, we only need to be showing a few. If it's not the final answer, still just show the 3, just do a dot, 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 and don't round yet. But here's this snazzy trick, and it can be really time-saving. My 0 is on my screen, or if my max or my intersection or my min was on my screen, if I go immediately, not immediately, but the first thing I do is hit second quit, second mode, and then I hit, and there could be all sorts of junk. I still have something from this last question. I still have 55.56, etc. on there. But I haven't typed anything. All I've done is quit the screen. If I hit stow right away, STO right above the on button, if I hit stow, and if I hit a letter, guess what it stores? The number up above? It stores the number from the graph. So right now I've stowed 6.7346938878 as my letter A. So I can go ahead and say, sweet, I need the velocity when. Okay, let's go ahead and plug in. So negative 9.8 times, and I have my number from right up above, or I can just hit alpha A. And then I can go ahead and do plus 33. So let me show you that really quickly just because it is super helpful, and even on the AP, hopefully you'll be able to use this at least once or twice or 5 times. If you, once again, have a function in your calculator in your y1, and this one I had my negative 4.9 x squared plus 33t, I had my position function. And I was just in Zoom Standard, which might have worked and might not have. But this one, it happened to work because I could see there he is. I can see the 0, but you might want to play with the zoom a little bit. If you go find the 0, answering the questions I just talked about, go find the cursor. I need this cursor to be to the left, or in this graph, a little bit above. It's going to go all the way up to the highest height. It's going to come back down. I can watch my numbers. It's still going up. Oh, now it's coming back down. Here it comes. Almost. I need to get in between negative 10 to 10. There he is. He's chilling. I'm going to answer the left. He's going to go past the 0, answer the right. Okay, do you see how the 0 is on the screen? You tell me, how do I stow it to use it?
Second quit.
Second mode to get to quit. Stow.
C.
You can call it whatever you want. A, B, C, D. Oh, don't call the number, call the letter. But if I stow it, there were extra numbers that were up there in my graphing calculator, but it's going to stow exactly what's coming from my graph. Which is pretty snappy. So I can go ahead and do my negative 9.8. I didn't have to write anything down. I could show my work by showing some of it. If I didn't have to write anything down, I could go ahead and use my alpha C. And when I use the C in the equation for my velocity, which I'm plugging into my V of t equation, I get 9.8 times the time plus 33. It's going to go ahead and steal that and put it in, and I have negative 33. Weird, huh? Now, here's a dilemma with velocity and speed. Velocity is negative 33. So kiddos, does your speedometer show positives and negatives?
No, we don't.
Ooh, well, if your speedometer doesn't show positives and negatives, guess what? Speed has no regard, disregards direction. It's the absolute value of velocity. So think your speedometer, always positive. Cool. So if they want the speed, what am I going to put?
Just the positive.
Just 33. Just positive 33. So speed is going to equal 33 meters per second. Now, is there something in our motion packet we might be able to fill in his speed? What can we fill in? We've already filled in hit the ground. We filled in position, velocity, acceleration. How about initially? What do we know about initially?
Initially,
T equals 0. Good. That's when time is 0 at the very beginning of the situation. Now, the very beginning might be 10 a.m., but we'll still say T is 0 because that's our reference point. And then like 2 hours later, then T equals 2, etc., etc., etc. So initially is when time equals 0. You guys keep going through the list while I pass out your forever quiz from after Christmas break. Finally, I was going to get all updated with all sorts of stuff this week, which isn't really that many. What do we have? Quoting, forever quiz, the integration quiz after we grade it. A spot check. There aren't going to be that many grades, so make sure you're staying on top of things. Spot check for 4.1321. But go ahead and check out these grades. We'll pass them all up in just a moment. I want you guys to see the grades before they get hidden in your test folder. But what other blanks can you fill in? Keep looking. Sam, keep
at rest is the U T equals 0.
Sarah. Austin. Karen. And remember, your coding has some bonus, hopefully, if you did above and beyond. So that's going to definitely help your grades look nice, despite what this one looks like. But some of you need to look at this and be like, how well do I know my forevers, and do I need to keep studying? The answer is probably yes. Probably yes.
Oh, that's not that bad, actually. I can multiply.
I want you guys to look at the bonus really quickly and figure out why I could not take what I wanted to take as the correct answer as the correct answer. I wanted to take e to the n as the correct answer. How did I write the bonus wrong? What was inside the parentheses?
1 plus
So then,
N.
how did I write this wrong?
Is this supposed to be changing?
So the n power was actually right. This is from forever card number 3, I think. That was right. What was wrong?
It wasn't correct. It
Oh,
was-
is the N power. I think I remember you told me that the N should be X.
One for the quotes.
Oh, yeah. Sorry. Sarah, you were good. It was, or whoever else said the n power. That's wrong, but also, did I do the limit as x goes to infinity or as n goes to infinity?
X.
Oh, I did do x. Okay, good. Well, I did that right, but the problem was I had an n here instead. If it was the limit as x goes to infinity.
So you'll give everyone the full bonus points?
No, I graded it correctly. I'm trying to show you why I graded it the way I graded it. If it was to the x power, this would be e to the n. If it was to the x power, this would be e to the n. Or if this was all switched, people have also seen it this way, where it's like, that's an n, that's an n. This is what I was thinking, that's an n. This should have been an x. Then it would be e to the x power instead, and that would be appropriate. But the way that the quiz was, it should have been e to the n power, but only if I had written the question correctly. I like mix the two notations. This is e to the n from your forever card. The dilemma is, what would this one be? It'd be 1 plus, if n is a constant over infinity, well guys, who wins? Bottom, so this is 0, so it'd be 1 plus 0, all to the n power. This would just be 1 to the n power, n is a constant. It'd just be 1. So anybody who put 1 and showed me why, you would have gotten the full plus 2. Anybody that put an e to that, and I was like, oh, I really want to take all of this, and I can't. I think I still gave you a plus 1 or a plus a half, depending on what you showed me. Like if you just put an e, I might have done a half. If you did an e to the n, I probably gave you a full 1 point, but you didn't get both. Does that make sense? So on the bonus, it was, I mixed two notations when I was writing it really quickly. Technically, this one where you would have had 1 plus 0 to the, if the x is in the exponent, it's 1 to the infinity. There's my indeterminate. And through L'Hopital's, which you could have done if I had written it correctly, or just through your forever card, then you would have gotten to e to the n eventually. Okay, so this is what I wanted to do. I apologize, I wrote the question wrong. I wanted to make sure you guys understood the grading as to how that happened. Any other questions on grading real quick?
No.
I tried to get partial credit where I could. Let's go ahead and pass those up so we can get them filed away today. That'd be really helpful. But the forevers, a lot of you did quite well. But a lot of you missed little things here and there, and it's very normal. I don't want you to think it's not, but we do need to include. Because these are still as important as they were before. Okay, thanks guys. What else have you been able to fill in? At rest, we already know t is equal to 0. Oh, sorry, initially it's t equals 0. At rest, what equals 0? Velocity, because you're not moving. You could say velocity and speed, but if velocity is 0, speed would be 0 also. So velocity equals 0 when you're at rest. You could also put some other things like the maximum height, like we just saw with the projectile, when you have something being projected up and it's falling back down, the maximum height, the velocity will also be 0 because of what we already talked about with IVT. What did you guys answer for number 4? We have it filled in. If the velocity is positive, the particle is moving to the
Right.
The velocity is, how about number 5?
Negative.
Negative, good, then the particle is moving to the left. How about number 6, average velocity? Very similar to average rate of change. What do we divide? Change in
Position?
change in time is the bottom. dt is the bottom, but dx, change in position. Change in position gets divided by change in time, which is why average velocity, which is average rate applied to motion, f of b minus f of l over b minus a, would be x of b minus x of a all over b minus a. Average velocity is just average rate applied to position. Instantaneous velocity is the velocity at a single moment in time. I would make that notation position prime, right? Instantaneous velocity. That would be like the derivative of position. So it's the difference between average velocity using the change in times to help us versus instantaneous at one instant. That would be take the derivative, plug in. How would you answer number 8? If the acceleration is positive, then the blank.
Velocity.
But
Well,
why? You can raise a hand and say, why would velocity should be increasing, Sean?
So it's going back to what we learned last semester with the second derivative and the first derivative, and how when the sign changes, how that indicates the other. So if the acceleration, which is the derivative of velocity, is positive, then we can say that the function, which is velocity, is increasing.
Good. The increasing decreasing test says that a quantity is increasing when its derivative is positive. So you have to see acceleration is velocity's derivative. So of course it must be positive in order to have the velocity be increasing. Or the velocity will be increasing when its derivative is positive. So how do you guys feel in number 9? Good. So when the acceleration is negative, then the derivative of velocity is negative, which means velocity is decreasing. Number 10, how do you guys fill in order for a particle to change direction, the velocity must change signs. Not necessarily acceleration. You could be putting your foot on or off the accelerator pedal, right? You could be putting your foot on or off, and you could still be moving to the right. So acceleration can be positive or negative, and you still be moving one direction. The point is, what's the sign of your velocity? All right, that was all the clues on the first page. Let's keep going now. Let's see what we can do and what we can't do, because the motion packet is due tomorrow, but the dilemma is you can't do all of it yet. We haven't learned definite intervals yet, which means that even though you can do some of this, we are going to have to save some of it until later. Let's go ahead and
Wait, what about the next?
left.
so the rest of it will be due by the end of the chapter, but not necessarily tomorrow. Okay, first of all, without us answering, I want you guys to go through and make some stars with me, okay? Number 1, put a star. That's something that you can do right now. Number 1, put a star. That's something you can do right now. Number 2 is stop. Number 2 is something you can do right now. Number 3 is interesting. Something you can do right now.
Oh yeah, you can do
And
the
number
fourth
4 you can do right now. So this entire FRQ, this entire example number 1, I want you guys to make sure that that's one that you realize that we are doing tonight for tomorrow. Okay? Number 1, you're looking at a sign of velocity. Number 2 might have something to do with particle at rest. Derivative is equal to 0. Might have something to do with MVT rules. Might have something to do with MVT rules. Wait a minute, at rest.
That's right.
I would do IDT. IDT might be an easier one. I didn't look at what was in the table first. Number 3, approximation. You might want to think average. Average velocity. I should say average rate. This one is velocity prime that you're trying to find the approximate of. So you're going to find the rate but using an average. And then number 4, I would think MVT rules. Just a couple hints to keep in mind. We'll talk about them at more length a little bit later. Example number
Now, you can do
2.
this one too. Pretty much the whole thing, I think. Because just like
Yeah, number 2
determining
is also
information
good.
from the graph.
I was making sure it had nothing to do with area under the graph. Usually when you see a graph like this on an AP FRQ,
It's actually maybe.
not specifically though. You might be able to apply it, but not specifically. This isn't quite as extensive as an AP one, but it's a great question as far as the ideas that'll definitely show up. Example number 3.
Oh right, I did this one. Pretty sure you can do this one too. It's like one of the.
I want you guys to go ahead and put little parentheses around number 4. That's one that we're going to leave until later. Number 4 we're going to leave until later. We're definitely going to cover, we definitely need to cover, but it's not quite yet. It's not quite yet.
We can do that. Number 11 on the very top. Beginning. Did do.
Oh, I skipped one, didn't I?
Number 11 is like that. It's total business travel.
Okay, number 11, go ahead and put little parentheses around it.
Where is 11?
On the very first page, I didn't have it copied on my notes, that was my number 11 on the very first page. I forgot there was number 11. Put quick little parentheses around that as well. Okay, we're going to go ahead and pause real quick and time out. I do want us to talk about homework. That's technically what's due today. With any extra time, we'll come back to the motion packet and maybe go over a little bit all together. But those are the problems I want you guys to try tonight for tomorrow. Examples 1, 2, and 3, except for the ones I put the parentheses around. Not that it'd be impossible for you to do the parentheses ones, but it would be quite difficult without some direction from me. So, homework last night, how'd you guys do? What questions do we have?
63, please.
63 and 64.
Just that back. That back keep going. Let's go through it.
On my sheets, this is 4B, right? No, 4A. Whoa, we are not in the latter end of integration. Alright, what are you given in number 63 as in pulling up the book? Alright, hold on, Nathan, a little bit louder. What are we given in number 63?
I think if I have it copied down right, it's the acceleration is equal to A. They don't actually give you an acceleration.
Okay, so they give you acceleration as like a constant?
Oh, constant, that's a difference, yeah.
Okay, but they didn't establish the constant, or they didn't give the number? Okay. So then as they gave us a constant for acceleration, then they went on and wanted us to use that constant, but we're not going to actually have a number plugged in. What did they ask us about first?
Position, there you
They want
go. They want the acceleration.
They want us to find the acceleration? So they give us acceleration as a constant. They had to give us something else. They give us a graph or a table.
They gave us 13 seconds.
Oh, they did give us some clues. Okay, that's what I was looking for, is what clues they gave us. So we know acceleration is a constant, but then what was 13 seconds indicating?
30 seconds to accelerate from 25 kilometers per hour to 80 kilometers.
Okay, so they told us like a beginning, is that a velocity, right? Does that make sense? They give us a beginning velocity, and then they give us where the velocity goes or changes to after an amount of time. So, I don't think they give us acceleration as a constant.
Assume the
Assume
the acceleration stuff.
Oh, I didn't see the timeline. Okay, and that's why I said acceleration is good. So if the acceleration is constant, that means one acceleration the entire time. Kind of like cruise control in the sense of staying the same, but cruise control is when velocity is staying the same. Acceleration is your foot is putting the right amount or the same amount of pressure on the speedometer, not the speedometer, oh my goodness, on the accelerator, on the gas pedal. So you have a constant pressure on the gas pedal, so your acceleration is pushing the velocity at the exact same rate the whole time. Because we just talked about how in your motion packet, I had you star something, and the starring of the something, if you want to look at it, this was question number 1, part 3. Question number 1, part 3. They ask us to find an approximation for v prime of 10. What's v prime? Acceleration. At 10. What's the problem with acceleration at 10? Do we have 10, first of all? No. Do we have acceleration, second of all? No, but how do you think about acceleration? Acceleration is velocity prime, but velocity prime, another way of writing that is dv dt, which means change in velocity over change in time. Now this is instantaneous. Average would say, hey, okay, well, if I can't do instantaneous, I can do average. And so I could say that acceleration, which equals v prime, could be approximately found by v of b minus v of a all over b minus a. Now in this example, when do they want the acceleration? At 10. So I would change the t's to be 10. So I would say, okay, I want acceleration at 10, which is v prime at 10, but why am I putting an approximate? If I can't do 10, what can I do when I plug in average?
12 and 8.
I can use 12 and 8, good. So I'm going to do v of 12 minus v of 8 all over 12 minus 8. I'm going to get, on average, what seemed to happen, what change seemed to happen between 8 and 12. And that's going to be approximate for what's happening at 10. But question, how can they, in the book problem, in number 63, how can they ask us to find the actual acceleration, not approximate, not estimate, not be kind of close, but find the acceleration when they give us a change in time and change in distance? Why isn't it approximate? When I find it by change in velocity, when I plug into my formula for average acceleration, how can I say it's the actual acceleration? Is acceleration changing? And since acceleration isn't changing, since it's staying constant, the average will equal the instantaneous. Since acceleration isn't changing, the average will equal the instantaneous. The average will equal the instantaneous. So therefore, for letter A, since the acceleration is remaining constant, when I find that 80 kilometers per hour minus 25 kilometers per hour, the change in my velocity, so delta V over delta T being 13 seconds. Ooh, struggle. Hold on, can I just divide?
5.
Oh, you don't have the same unit.
I'm going to have kilometers per hour per second, right? So I could go ahead and solve for this. That wouldn't be totally bad, because 80 minus 25 would be 60, 55, and 55 divided by 13 would end up being
5.
4 point something gross. But the dilemma is when I get 55 over 13, I have kilometers per hour seconds. What did they tell me to get this into? But before we even do that, kiddos, this is a very precise answer, because if this is the average acceleration, if this is what was going on that entire time and the acceleration was constant, okay, I found my acceleration, I'm good. Since acceleration wasn't varying, I don't have to worry about it being different than the derivative. How do I do dimensional analysis? I need to build some bridges here.
Yes.
I need to get rid of kilometers and change it to meters. How many meters in a kilometer?
1,000.
Oh,
So I'll get rid of that, right?
mhm.
What else need to get rid of?
Gotta get rid of the hours.
Yep, because that second's fine, but that hour is not. So I'm going to need to go ahead and get rid of 1 hour. Not hours squared, just 1 hour. How many seconds? Good. 60, 60. 60 times 60. So 3,600. Now I can go ahead and find it. So 55 times 1,000.
I'm gonna guess it's 55 or 550 or 460.
1.1.
Yeah. 1.175. Remember, always 3 decimal places, and I have meters per second squared. Per second, per second, per second squared. Now, what do we do for letter B? That's letter A, that's acceleration.
Okay. We gotta go
Distance?
backwards.
Yeah.
Let's
Gotta
go
go
back.
fast.
Since we have acceleration, can we
From
go all the way to position by integration now?
Yeah, we have to go 2 integrations, right? So I can go ahead and do velocity first of all. Velocity is going to be 1 integral of acceleration. Struggle though. What am I going to make my initial, because it's plus c, right? What am I going to make my initial velocity?
25.
Yeah, because it started at 25.
Okay, 25 kilometers per hour.
No, 7 meters per hour. Or no, 7 meters per
The what?
You can convert it to
7.
meters per second.
Do I need to convert this one too?
Less than 36 seconds. Is that 250 over 36?
And then meters. So that'd be 2,500 over 3,600, right? Which would be, 25 over 36, which would be 5/6. Does that make sense?
Oh wait, are you sure it's not 250? Okay.
It might not be.
Wait,
No, I think it's
holds.
Oh, 25,000. Sorry, I did 2,500. Yeah, that's not good. So it'd be 25 over 250 over 3,600. Over 36. 6.944. That'd be a fraction, so I don't have to write the nasty decimal. 125 over 18. Not sure that's really better. Okay. How do I get to position then?
Go again.
Go again. So I have 1.175 all over 2t squared plus 125 all over 18t. What's my initial position?
Yeah.
Pat, it'd be helpful to have you right now.
What?
We're talking about a car that can go from 25 kilometers per hour to 80 kilometers per hour in 13 seconds. We're curious as to what we would make the initial position when plugging into or when trying to find our position formula.
0?
We can make, even though the car is going to be somewhere, the car is going to be going in speed, we can always make the initial, if we want to, our reference point, aka 0. We can make our initial position 0 if they don't tell us that we need to measure it in reference to something else. We don't care how far the car was from a town or from a gas station or from another car. So we can just make it 0 and say whatever, starting from 0 and going how far. What are we going to do to figure out how far it travels in 13 seconds?
Go plug in that time. Let's
Plug it
go.
in, plug it in. It's an odd, we're not grading until tomorrow. You guys know what to do. We had to worry about dimensional analysis, we had to worry about converting to proper units. And we had to think through some of these different clue words, and it was a little tricky, I won't lie. Guys, you also have a question on number 64.
Constant deceleration.
64, let's think about 63 and try to apply it to 64 now. Sound good? And then Charlotte was saying number 71.
Oh.
You're going to integrate, right? To get to velocity and position using your clues. We're going to be able to grade that one tomorrow. So I would think about taking the integral to velocity and the double integral to position. 71, when you look at dp dt, what is that guy?
That guy's good.
He's the derivative
Oh,
of
is that
what?
momentum?
Uh,
Is that what the rate is? Are we doing momentum?
He's the derivative of
Oh,
population.
population.
So he's the rate.
So he's the rate of change of population, right?
So it's double track?
So if it says population increasing,
That's what it is.
this is P prime.
So let's do a degree. Let's do some
Can we
sign
do a
checks.
sign chart?
But is that a double part?
No, this is d, not d squared p dt, this is just dp dt.
But I saw the green of
No, it's okay, rate of growth is this. Does that make sense? So population is p, the rate is this, the derivative of p. So this is p prime. So if you want to think about it, p is like our distance, if you're thinking in terms of motion. P prime is like our velocity or our rate. So we want to think about sign chart. We want to think about absolute min. Ooh. And we want to think about integration. To go back. Does that make sense?
Yeah.
Alright, play with your book first, and then go play with your motion packet. We will go ahead and grade homework and see how you guys did tomorrow.
Because see, there's a bunch of indefinite here in the packet. Are we just supposed to skip them? I mean,
example 1, 2, and 3.
oh no. Oh, I've made a mistake. Oh.
Didn't you notice this today?
I wasn't paying attention. Oh.
Tyler, stop on the packet and go play on bookwork tonight.
Yeah, probably. But I finished like most of mine.
Good job.